So, looking at lesson 6, L'Hopital's rule. So you guys remember when we were doing limits and we ended up with these indeterminate forms? And I said, it's tempting just to say it doesn't exist. Well, sometimes it does exist and sometimes we can find it. So, to do this, L'Hopital's rule is a great tool for finding limits that are often difficult to evaluate. It can also help to determine limits at infinity for asymptotic behavior. We'll use it for curve sketching in the next section as well. When evaluating limits by direct next chapter, next unit, we won't, this is the last section, but of unit 4. But in the next unit, we'll be doing curve sketching. When evaluating limits by direct substitution, there are 7 expressions known as indeterminate form. The first 2 are the only ones we're dealing with. These ones are Calc 2 and 3 things that you'll be looking at if you get to that point. Right now, we are only talking about 0 over 0 and infinity over infinity. Consider the limit of a quotient, the limit as x approaches c of f of x over g of x. L'Hopital's rule states that when f of x and g of x has an indeterminate form of the type 0, 0, 0 over 0, or infinity over infinity at c, then we can replace these by the quotient of their derivatives. So the reason we couldn't do L'Hopital's rule before is because we didn't know how to do a derivative. Now that we do, we have another tool that we can use to find limits. So, assuming f and g are differentiable on the open interval, and that the derivative of g of x does not equal 0, then we can state right here that the limit as x approaches c of f of x over g of x equals the limit of their derivatives. Now, why can that be helpful? Well, sometimes that will actually let us do a direct substitution. And if it does, then it's easier to find our limit. The thing is, you have to make sure these conditions are met. 1, the derivative at c cannot equal 0 in your denominator. If so, then the limit is undefined. No oscillating functions. So do you remember we had some oscillating functions where they went up and down and up and down and up and down? Can't have oscillating functions. And then also these two cannot equal plus or minus infinity. So we will talk about those here shortly. It is super important that you use proper notation when you're using L'Hopital's rule. And you state explicitly the conditions are met. Okay? In order for L'Hopital's rule to be used on an AP Calc test, students should show proper procedural steps and notations. Explicitly show that the numerator is 0, infinity, or negative infinity. Explicitly show that the denominator is 0, infinity, or negative infinity. You cannot just say that the limit as x approaches c of f of x over g of x equals 0 over 0. You cannot say that. You have to actually show the limit as x approaches c of f of x and the limit as x approaches c of g of x. You may want to state that the limit is indeterminate form because they are both infinity or 0, plus or minus infinity. By L'Hopital's rule, the limit as this, and find the limit using proper notation. So let's go through and actually state explicitly what we're supposed to do. So back to limits. When we have this, we try a direct substitution pretty much always, right? So if we're going to do a direct substitution, you'd plug in your 5. You'd have 2 times 5 squared minus 9 times 5 minus 5. Here, this would be 25 times 2 is 50 minus 45 minus 5, which would equal 0. Is that fair? Here, if we did a direct substitution, you'd have 5 minus 5, which also equals 0, correct? So we know we would have 0 over 0, which is an indeterminate form. So we have to state the limit as x approaches 5 of f of x, so 2x squared minus 9x minus 5 equals 0, and the limit as x approaches 5 of our denominator, x minus 5 equals 0. Therefore, we have indeterminate form so by, and you don't have to state by L'Hopital's rule, but for practice we're going to. So by L'Hopital's rule, we know the limit as x approaches 5 of 2x squared minus 9x minus 5 over x minus 5 is going to equal the limit as x approaches 5, and we have to find the derivative. So the derivative of 2x squared minus 9x minus 5. What is that?
4x minus 9.
Yep. And the derivative of the denominator, x minus 5, is simply just 1. Now do a direct substitution again. You would have 4 times 5 minus 9. 4 times 5 is 20 minus 9. So what does this equal? 11. Now, other ways that we could have done that was we could have tried to factor the numerator, right? Yeah? So when we were doing limits, we tried to factor, we sometimes rationalized, yes? Those are some of the tools that we did. Now we have another tool, L'Hopital's rule, that we can do. So, some of them we couldn't factor though, remember that? Or we couldn't rationalize, or whatever the case was. And so we were kind of stuck. Now we aren't necessarily stuck. All right, let's look at this one. If we do a direct substitution, we'd have the square root of 4 plus 5 minus 3. And here we'd have negative 5 plus 5. So the denominator is 0. The numerator would be the square root of 9 minus 3, which would end up being 0 also, correct? So we have to state the limit as x approaches negative 5 of the square root of 4 minus x minus 3 over x plus 5 equals, nope. Sorry. Got to state the numerator's limit equals 0, and then the limit as x approaches negative 5 of the denominator also equals 0. Then we need to find the derivative of the numerator and denominator. I'm going to rewrite that numerator as 4 minus x to the 1/2, just because I think it's easier to do the derivative in that form. Does that make sense? So here, the derivative, we take down the 1/2. We do 4 minus x to the subtract 1 would be negative 1/2. And the derivative of the inside would be negative 1, correct? So we get negative 1 over 2 square roots of 4 minus x. Is that fair? And the derivative of our denominator, x plus 5, is just 1. Fair? So, we had an indeterminate form. So, by L'Hopital's rule, the limit as x approaches negative 5, the square root of 4 minus x minus 3 over x plus 5 equals the limit as x approaches negative 5 of the derivative. So you'd have the derivative of this over this, right? But when you divide by 1, it's just what was in the numerator, right? So negative 1 over 2 square roots of 4 minus x. And then we would try to do a direct substitution again. You'd have negative 1 over 2 square roots of 4 plus 5, right? So negative 1 over 2 square roots of 9, or negative 1 over 2 times 3. So our limit would be what? Negative 1/6. Fair? Okay. So, just because you do it once, if we do another direct substitution and we end up with another indeterminate form, you can do it again.
So you can keep deriving it.
You can. And sometimes you should. So, let's look at this. When I look at x squared, I immediately know what that is in my mind, right? It's a parabola. Okay. And when I look at this one, I also know what that looks like in my mind. Do you know what e to the x looks like? E to the x looks like this, right? E to the negative x then.
Would be flipped.
So e to the x and e to the negative x. So you need to start thinking in terms of that, so we kind of know what they look like. All right. So if we plug this in, if we plug in negative infinity, I'm not even going to put an equal sign there because it's not really equal. Here, negative infinity squared would be positive infinity. Is that fair? A negative times a negative is a positive? So this would be infinity, all right? Here, if I plug in negative infinity, I'd have e to the negative infinity. And e to the infinity is what I'm talking about, right? Which any number to an infinity is going to be infinity, right? Just going to get bigger and bigger and bigger. Do you agree? So we end up with that indeterminate form there, yes? All right, so number 1, the limit as x approaches negative infinity for x squared, which we know as x is going to the left for x squared, we know this is going to go up forever. Yes, as we go to the left, it's going to go to infinity. And we also know that the limit as x approaches negative infinity for e to the negative x, thinking of this is e to the x, e to the negative x was flipped, right? So as we go to the left, this is going up to infinity forever as well. So we have an indeterminate form. So by L'Hopital's rule, we know the limit as x approaches negative infinity of x squared over e to the negative x would equal, well, let's do the derivatives here. The derivative of x squared is,
2x.
and the derivative of e to the negative x would be
Negative e to the x.
negative 1 e to the negative x, right?
Oh, yeah.
Because the derivative of e to the x is just e to the x, but then we have to do the derivative of the inside. So we now have the limit as x approaches negative infinity of 2x over negative e to the negative x. Well, if I do a direct substitution here, I'm going to get what? Negative infinity. 2 times negative infinity is negative infinity. Here I'm also going to get negative infinity, aren't I? which again is an indeterminate form. So I have to state my limits again. The limit as x approaches negative infinity of 2x equals negative infinity, and the limit as x approaches negative infinity of negative e to the negative x also is negative infinity. So again, indeterminate form. So by L'Hopital's rule, we got to do the derivatives. The derivative of 2x is 2. And the derivative of negative e to the negative x would be positive e to the negative x, wouldn't it? Is that fair? Because it'd be negative e to the negative x, and the derivative inside would be negative, yes?
Yes, it just means plus 2 over e.
Positive e to the negative x.
Yes.
Yep. So the limit as x approaches negative infinity of 2x over negative e to the negative x equals the limit as x approaches negative infinity of 2 over e to the negative x. So if you were to do a direct substitution here, you'd end up with 2 over e to the negative infinity, correct? Or 2 over e to the infinity? When you divide 2 by some extremely large number, you get, do you remember?
0.
Yep. Any whole number divided by some large number. So we're talking about a limit, and because we're talking about a limit, it's going to go to 0, right? So 2 divided by 10, 2 divided by 100, 2 divided by 1 or whatever, right? It's going towards 0. Does that make sense? Okay. All right. Let's look at example 4. Why?
It's a lot of numbers.
It looks horrible. It's not. All right. So looking at this, because they're both polynomials, right?
I still don't like it.
So looking at this, we're plugging in negative 2. Yeah? If we plug in negative 2, we have negative 2 cubed plus negative 2 squared minus 8 times negative 2 minus 12, which would be what? Negative 8 plus 4 plus 16 minus 12. 16 and 4 is 20, and negative 20 is 0. Fair? Here, negative 2 cubed plus 8 times negative 2 squared plus 20 times negative 2 plus 16. So again, negative 8. Negative 2 squared is 4 times 8 is 32 minus 40 plus 16. So you'd have negative 48 and positive 48. So again, you get 0. So the first thing is, and I would even say, hey, I could define f of x as x cubed plus x squared minus 8x minus 12. And I could define g of x as x cubed plus 8x squared plus 20x plus 16. If I'm to define those, if I write those down, then I can say the limit as x approaches negative 2 of f of x equals 0, and the limit as x approaches negative 2 of g of x equals 0. As long as you explicitly define your functions, You can write them however, right? So since I named those, then I can use those names. Does that make sense? It's going to make my life easier because I'm not going to have to write all that out multiple times. So the second thing, since we had that, we had indeterminate form. So by L'Hopital's rule, we know that the limit as x approaches -2 of f of x over g of x equals the limit as x approaches -2 of, we need to find the derivative of f of x, right? So f prime of x would equal what? 3x squared plus 2x minus 8. Is that fair? And the derivative of g of x would equal what? 3x squared plus 20. So you could state there f prime of x over g prime of x, or you could write the functions in there, yes? But since I defined them, I could just state that right there. And then I try a direct substitution, yes? So if I try a direct substitution, here, if I try 2, I would have what? 3 times -2 squared plus 2 times -2 minus 8. Which would be what? 4 times 3 is 12. Minus 4 minus 8 is 0. And for g of x, I'd have 3 times -2 squared plus 16 times -2 plus 20. That'd be negative, or 4 times 3 is 12 minus 32 plus 20, which is also 0. So I'd have to state the limit as x approaches -2. And you could say f prime of x, or you could say 3x squared plus 2x minus 8, right? Doesn't matter which way you write it. Equals 0, and the limit as x approaches -2 of 3x squared plus 16x plus 20 equals 0. Indeterminate form. So by L'Hopital's rule, the limit as x approaches -2 of f prime of x over g prime of x, derivative of f of x over the derivative of g of x, equals, well, now I've got to find the second derivative, which would be 6x plus 2, fair? And the derivative of g of x, so the second derivative would be 6x plus 16, correct? So now I have the limit as x approaches -2 of 6x plus 2 over 6x plus 16. Or you could say second derivative of f over the second derivative of g, yes? Let's try to do a direct substitution. 6 times -2 plus 2 over 6 times -2 plus 16. This one's going to work. -12 plus 2 over -12 plus 16. We would end up with -10 over 4, which is -5 over 2. So that one, could we have factored it? Maybe. I don't know. I don't think so. I don't think you can factor that one. So you can see where L'Hopital's rule was helpful. You would have had to use the P over Q and find something that can divide out and all of that. All right, transcendental functions. So there's 2 special limits. Do you remember the 2 special limits?
1 minus sine
sine x over x.
Oh, close enough.
And the limit as x approaches 0 equaled 1. And then the limit as x approaches 0 of 1 minus cosine x. You were close. I just had the two switched. Over x equals 0. So when I look at this, because I know those special limits, I can see that I could separate this out and say this is the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 minus cosine x over x. And therefore, I can say this is 1 times 0, which is 0. Like, I know that because I know those special limits. But if you didn't, how could we do it? Well, you can do the L'Hopital's rule. So let's look at that. So the first thing is that we know that if we plugged in 0, thinking about here at 0, right one up 0, sine is 0, right? Because sine is your y coordinate, yes? So you'd have 0 times something, so it would equal 0. So the limit as x approaches 0 of sine of x times 1 minus cosine x equals 0. And we know 0 squared is also 0. So the limit as x approaches 0 of x squared would be 0. So indeterminate form. By L'Hopital's rule, we know that the limit as x approaches 0 of sine of x times 1 minus cosine of x over x squared would equal the limit as x approaches 0 of, we know the denominator's derivative would be 2x, right? Let's come over here and find the derivative of the numerator. We're going to have to do the product rule there, right? Make sense? So if I take the first one, sine of x, and do the derivative of the second, so the derivative of negative cosine would be negative sine, which would end up being positive sine x right here, right? Because you have negative cosine times a negative would be negative, and a negative is positive. All right, plus here we have 1 minus cosine x, and the derivative of sine is cosine x. So we would get what? Sine squared x plus cosine x minus cosine squared x. Fair?
How do you get the first part?
First one is sine of x times the derivative of this. So you have a negative, and the derivative of cosine is negative sine. So a negative and negative make a positive sine x. Because you have this negative times the derivative of this. Yeah?
Okay.
Okay. So sine squared x plus cosine x minus cosine squared x. Okay. If we do another direct substitution, here sine of x was 0 plus cosine of 0 is 1 minus cosine of 0 is 1. 1 minus 1 is going to be 0. And 2 times 0 is also 0, right? So we're going to end up with another indeterminate form. So the limit as x approaches 0 of sine squared x plus cosine x minus cosine squared x equals 0, and the limit as x approaches 0 of 2x equals 0. So again, we had indeterminate form. So by L'Hopital's rule, the limit as x approaches 0 of sine squared x plus cosine x minus cosine squared x over x 2x equals the limit. Now you can see that this is starting to help us, right? Because the derivative of 2x is 2. And so then we have to do the derivative of sine squared x plus cosine x minus cosine squared x. So the derivative of sine squared x would be 2 sine squared x, right? 2 sine x, but then the derivative of the inside would be cosine x, right? Think about sine x squared. You take the 2 sine x times cosine x. Here you'd have minus sine x, correct? And then here you'd have minus, but it's actually going to be plus, right? Because when you have cosine x squared, you have to do the derivative of the inside. I didn't leave myself enough room there. So here you take the 2 down in front, and you'd have cosine x. The derivative of cosine is negative sine, so you'd have positive sine x there. Because the negative and negative make it positive. So we have 4, yep. 2 sine x cosine x and 2 sine x cosine x is 4 sine x cosine x minus sine x. And then if we do a direct substitution here, we would have sine is, you'd have 4 times sine is 0 times 1 minus 0. So you'd get 0 divided by 2, which is 0. So you can see how remembering those special limits might be helpful, because that would take a lot more time. Yes? But it's doable. All right, let's look at example 6. Limit as x approaches 1 of, so let's plug it in. Here we have natural log of 1 minus 1 plus 1. Natural log of 1 is 0, right? Mm-hmm. Think about log base e of 1. That's what ln is, natural log, right? Log base e. E to what power gives us 1?
0, okay.
Anytime you have 1 here with logarithms, it's always going to be equal 0. Because the only exponent you can get to equal 1 is 0. Okay. Over here, e to the first minus e is still 0. So the limit as x approaches 1 of natural log of x minus x plus 1 equals 0, and the limit as x approaches 1 of...
Wait, how do we get e to the 1? E to the 1 is 0, and then 0 minus
You plug in 1 here,
Yeah,
e to the 1
e to the 1
is just e,
oh,
right?
e to the 1 is e.
and e minus e is 0. Yeah. Anything the first power is just itself. Yep.
Oh, right. Duh. Okay.
All right. So we had an indeterminate form. Do you agree? All right. By L'Hopital's rule, the limit as x approaches 1 of natural log of x minus x plus 1 over e to the x minus e equals natural log, or limit, sorry, as x approaches 1 of, all right. Natural log of x minus x plus 1, derivative. Natural log of x, the derivative is 1 over x, correct?
Mm-hmm.
Minus 1, yes?
Hold up, Okay, yeah.
And then the derivative of e to the x minus e. Well, the derivative of e to the x is just e to the x, correct?
Yeah.
And e is just a number, so it's 0. So you just get e to the x. So we have 1 divided by x minus 1 over e to the x. We can try a direct substitution again. When we do that, we would have, what, 1 over 1 minus 1 over e to the first power, which would be what, 1 minus 1 divided by e? Or 0 divided by e, which is 0. Questions? You're just combining a lot of stuff that you already know, right? All right. So looking at this one. Now, looking at this one, I immediately can see that I have a polynomial all over a polynomial, and it's going to infinity. Yeah? And so when we do that, you can use your knowledge of rational functions and asymptotes. Remember those? Where if you have the same degree,
Oh, it goes to 0.
it's 9 over 12, right? If you had 1 degree less in the top, it was, well, if it was less in the top than the bottom, then it was 0. And if the top was larger, you had,
Slant or
right. So when you had the slant asymptote, it might be easier to use L'Hopital's rule, right?
So this is literally just 3 over 4.
It is. That's right. But if you didn't recognize that,
Yeah.
right? If you didn't recognize that, you would have to do a direct substitution, and you'd have 9 times infinity squared
Oh wait, I should write this in.
plus 10 times infinity minus 3 is going to be infinity, agreed? And the denominator would be 12 times infinity squared minus 4 would be also infinity, yes? So, the limit, and I'm going to define these because I don't want to write, well, I guess it's not that big of a deal. I'll just write them out. 9x squared plus 10x minus 3 equaled 0, infinity, not 0. And the limit as x approaches infinity of 12x squared minus 4 also was infinity. Indeterminate form. So by L'Hopital's rule, the limit as x approaches infinity of 9x squared plus 10x minus 3 over 12x squared minus 4 would equal the limit as x approaches infinity. What is the derivative of the numerator? 18x plus 10? Fair? Over 24x, correct? But if you do a direct substitution, you're going to get infinity and infinity again. Do you agree with that? So, again, the limit as x approaches infinity of 18x plus 10 would equal infinity. And the limit as x approaches infinity of 24x would also equal infinity. So we have an indeterminate form. And by L'Hopital's rule, we know that the limit as x approaches infinity of 18x plus 10 over 24x would equal the limit as x approaches infinity of 18 over 24, which would be 18 over 24, which reduces to 3 over 4. So, you might want to take note of knowledge of rational functions, and asymptotes. Right? So when the degrees are the same, we have y equals a over b, or in this case, y equals 9 over 12, which equals 3/4. Right? Make sense?
And then whenever the denominator is larger than the numerator, it's 1 or 0?
When the denominator is larger, it's y equals 0.
And then when it's 1.
1 greater. If the numerator is 1 greater, then you've got a slant. Yep. Okay.
Or there's more.
Huh?
There's more.
There is more. But we're close.
There's more.
What time's the class get out?
36, I think.
Yep. So on, yep. Okay. On these, we're gonna kind of skimp over example 8. It's a lot like what we've already done. It's a whole lot like the one where we had a number divided by infinity. That's what it ends up being, which is 0, right? Any number divided by a large number. So that's going to be the same type of thing. You do have to consider, like, what does it look like, right? Let's jump down to example 5 or 9 here. It says the table below gives values of a twice differentiable function y equals f of x. Use the table to find the limit if it exists. Justify your answer. So if we look at this, if we are to do a direct substitution, the limit as x approaches -2 of f of 3x plus 2 would equal here 3x plus 2. We're plugging in a -2, so you'd have f of 3 times -2 plus 2, which would be f of, what, -6 plus 2? Fair? Which is f of -4. What is f of -4? 0. And the limit as x approaches -2 of x squared minus 4 would be -2 squared minus 4, which is also going to be 0. So we have indeterminate form. So by L'Hopital's rule, we have to find the derivative of the numerator, f of 3x plus 2. So remember, you do the derivative of the whole, so f prime of 3x plus 2, times what's inside. So the derivative of the inside is 3. All right, so the limit as x approaches -2 of f of 3x plus 2 over x squared minus 4 would equal the limit as x approaches -2 of f prime of 3x plus 2 times 3. I'm going to put the 3 in front. Over the derivative of my denominator would be 2x. Yep. All right, so then let's try to do our substitutions here. The limit as x approaches -2 of 3 times the derivative of f of 3x plus 2 would be 3 times f prime of, what was that? -4. So we'd get 3 times the derivative of f at -4 is 3 times 8, which is 24, correct? And the limit of our denominator at x equals -2 would be 2 times -2, which is -4, correct? So 24 divided by -4 is -6. Make sense? Okay, we will finish, example 10 and 11, quickly on Tuesday. You'll have a little bit of time on Tuesday to, kind of finish up 4-4 if you need to. We'll start reviewing 4-4 on Tuesday. And then Wednesday and Thursday we'll review for Unit 4 test. Friday will be the start of your Unit 4 test.
I won't be here Thursday or Friday.
Okay, you'll just have to finish it next week.